Good morning students. Today we are going to discuss few topic from chapter 4, and the chapter 4 is your moving charges and magnetism. Now the first topic which we are going to discuss is your magnetic field on the axis of a circular loop carrying current. Now you see this is your circular loop through which the current is flowing, and the direction of current we have specified with the symbol capital I. Now we have considered a point at a specific distance from the center of the loop, x. The distance is x from the center of the loop, and the specific point where we have to define the magnetic field due to the circular loop carrying current. Now if you see the Biot-Savart law, you will see that dB is perpendicular to IDL and R, if you see the vector form of the Biot-Savart law. Now here what we will do, we will consider a small element of length dl, which we have specified in the figure as AB. Now due to that small element AB, basically it is a current carrying element, we will try to find the magnetic field at the specific point, which is at a distance x from the center of the circular coil. Now once we find the magnetic field at that specific point, what we will do, we will integrate considering the whole current carrying loop to define the magnetic field at that specific point. Now let me try to find the magnetic field at that specific point, which is at a distance x from the center of the circular loop due to the current carrying element IDL. Now if you see the Biot-Savart law, magnetic field is perpendicular to the plane containing IDL and R as per the definition of the cross product. So if we consider dB is the magnetic field due to the current element IDL, then definitely dB is perpendicular to the position vector R vector. So like that we have drawn the figure. dB vector and R vector is at an angle 90 degree. Now dB has his two component. One is along the x-axis, which you have defined as your dBx, and another one as dBy, which is along y-axis. Now if we consider the element diametrically opposite position, suppose it is at up, the element is up, which you have defined AB. Now if we consider another element which is diametrically opposite, and if you try to draw the figure, you will see that the field acts downwards, and it has two components. One is your dBy. dBy is opposite to the direction as we are discussing for the element AB, but dBx is along the same direction as the direction specified for the element AB. So you have seen that if you consider any two diametrically opposite elements, the component, basically y component, balances each other, and only you do have x component. So x components get added up if we consider two diametrically opposite element. So in this way, if you see whole current carrying loop, you will see that for every element there is a diametrically opposite elements, and for that y component balances each other and only x components get added. So if you have to define the magnetic field at that specific point, what you have to do, you have to add up the x component of the magnetic field for the current carrying element. So if you add up the x component of the current carrying element, then you will get the magnetic field at that specific point for whole the current carrying loop. So let me try to specify the mathematical part. So number one, magnetic field at that specific point due to the current element AB is your mu naught by 4 pi IDL. Now sine theta angle is your pi by 2. R and element makes an angle pi by 2. That's why theta is pi by 2. So IDL sine pi by 2 by R square. We are considering the scalar form of the Biot-Savart law. So mu naught I by 4 pi dl by R square. Now dB vector has two components, one is your dBx and another one is dBy. So as dBy cancel out for every diametrically opposite elements and dBx is added up, that's why we are considering dBx here. dBx is your dB cos theta, if theta is the angle made by dB vector with x-axis. Now if you see the diagram, then the triangle, if we consider with the angle 90 minus theta, basically if it is theta, then this angle is 90 minus theta. I think it's very simple, 90 minus theta plus 90 plus theta, so theta goes up, it is your 180 degree. So we have used the simple geometry. So cos theta, you can write sine of 90 minus theta, is not it, because sine of 90 minus theta, if you go by ASTC rule, it comes out to be your cos theta. So sine of 90 minus theta is your perpendicular by hypotenuse. So perpendicular is your r and hypotenuse is your small r. So small r, you can apply Pythagoras theorem. So it comes out to be your root over r square plus x square. So cos theta equal to capital R by root over r square plus x square. Now as you have to sum up the x component, so the net magnetic field at that specific point due to the current loop is your b sigma dBx. So sigma we have replaced by integration sign by considering the uniformity of the current carrying element. So integration dB cos theta, so dB is your mu naught I dl, mu naught I dl by 4 pi r square. So mu naught I by 4 pi square is constant, so we have taken out. So dl cos theta. So cos theta we have taken outside the integration. So you do have dl. So dl is nothing but is your circumference of the circular loop, that is your 2 pi r. Now cos theta is nothing but is your r by root over r square plus x square. So it comes out small r square. If you go for this one, then small r square equal to r square plus x square. So r square plus x square root over r square plus x square 2 pi r. So r square plus x square 3 by 2. So 2 pi goes 2 pi and 4 pi goes up. So you do have only 2 mu naught I r square by 2 r square plus x square 3 by 2. So this is your magnetic field at that specific point at a distance x from the center of the current carrying loop. So if you substitute this expression considering x equal to 0, it means you are defining the magnetic field at the center of the current carrying loop. So it comes out to be your x equal to 0, so mu naught I r square by square goes up, that is your r cube, so mu naught I by 2r. Now if you consider the loop is of n turns, here we are defining for single turns, then what you have to do, you have to multiply this expression by n. So ultimately you will get b equal to mu naught ni by 2r. So this expression is very important for the numericals, but you must have to know how it comes out, because sometimes in exam it is asked to derive the magnetic field at the center of the current carrying loop. So you have to proceed like this, and you know better that statement does not carry any marks, rather expression is there. So try to concentrate on the expression, and statement part you can make and write once you understand. Now next topic which you are going to define is your Ampere's circuital law. So before explaining, let me read out. It states that the line integral of the magnetic field around any closed path in free space is equal to the absolute permeability times the net current passing through any surface enclosed by the closed path. Now that is your closed integral. This is the symbol for closed integral. The b vector dot dl vector is your magnetic flux, so mu naught I. So this one we have to prove by considering this figure. Now we are considering a straight conductor carrying current I. So if you consider that your right hand pointing thumb as your direction of current, then the curled finger gives the direction of the magnetic field. So here what we have done, we have considered a small element Mn, that is your dl. So dl vector and b vector is in same direction, and r is the circular loop you can consider. Now I is the current carrying wire enclosed by the closed loop. So if I ask you to define closed integral b vector dot dl vector, then b vector and dl vector are in same direction, so b dl cos 0 degree, so b dl, so b comes out, that is your b 2 pi r. Now if you see the application of Biot-Savart law due to infinite long carrying current, then you will see that the expression for the straight conductor carrying current at a distance r is your b equal to mu naught I by 2 pi r, the previous class. Now if you substitute it here, you will get mu naught I by 2 pi r, 2 pi r, 2 pi r goes off, so you do have only mu naught I. So this is the proof of the Ampere's circuital law, and this part is very important. So please go through this part. Now before discussing next topic, solenoid, let me consider the node part. So you have seen that as and n we have written. So if current flows in clockwise direction, then that phase behaves as a south pole, and if the current flows as an anti-clockwise direction, then that phase behaves as a north pole. So let me try to we have to use this concept here, solenoid. So a solenoid, what we have written, I think most of you know what is solenoid, and probably you have seen. So what we have written, let me read out. A cylindrical coil of many tightly wound turns of insulated wire with diameter of the coil smaller than its length is called a solenoid. So figure 1 we have shown, this is the axis of the solenoid, and P is the specific point on the axis well inside the solenoid, and I is the current flowing through the wire which we have used to construct the solenoid. Now the second figure 2, you see we are not considering that curve part, rather we have considered two straight line, and because the wounding is very close to each other, that's why we can consider this is nothing but an straight, and P is a point where we have to define the magnetic field. So so we have shown that the south pole is clockwise direction current and north pole anti-clockwise. So if one phase behaves as a north, another as a south, depending on the direction of current, then the direction of magnetic field you can easily define from north to south. Let me apply Ampere's circuital law for this closed loop A, B, C, D, that small one, b vector dot dl vector. So you can split A to B, b vector dot dl vector, B to C, b vector dot dl vector, C to D, b vector dot dl vector, D to A, b vector dot dl vector. Now all these goes off except A to B, b vector dot dl vector, because A to B is inside the solenoid, and B to C and D to A, these are perpendicular to the magnetic field, so goes off, and C to D, as it is outside the solenoid, you can neglect that term. You do have only A to B, b vector dot dl vector. So b dl cos 0 degree because it is along the direction of the magnetic field. So dl is nothing but is your from A to B, if you consider it is your L, so bl. From Ampere's circuital law, this closed integral b vector dot dl vector equal to mu naught times the current. So if you consider L is the portion of the solenoid, so it has many turns. So if small n is the number of turns per unit length, then the total turns will be nl, and if I is the current in each turn, then mu naught nl I. So b vector dot dl vector, you see as per before, bl, it is bl, and mu naught nl I. So what happened, ll goes off, so you do have only b equal to mu naught ni. So this part is very important. Sometime in exam it is asked, find the magnetic field inside the solenoid, or state and prove Ampere's circuital law. Or this topic is also very important, magnetic field on the axis of a current carrying loop. Please go through, and if you have any doubt, any query, you can ask. So this is all about. Thank you.